Okay, the focus of this video is going to be on linear dependence relations. But before we get there, I want to revisit the idea of span because people have problems with this. All right, I found this picture on the internet. Here we have a plane and two vectors, the blue vector, this blue vector up to here, and this red vector up to here. And these two vectors are in the plane. They lie in the plane. Now I have this other vector, this magenta vector, which also lies in the plane. Now, what we have here is this blue vector being scaled back and this red vector being scaled up, such that if I follow first the scaled back blue vector and then follow the scaled up red vector, I reach the magenta vector. This is called a parallelogram law. You can see there's a parallelogram. If I follow first the blue vector and then the red vector, this side here is parallel and equal in length to the scaled up red vector down here. So by adding the blue vector and the red vector, I add the blue vector and then add the red vector, the tail of the red vector at the head of the blue vector. It makes a parallelogram. Now we've talked about commutativity. We could do the red vector first, and then this side represents the blue vector. You can see it's the same direction and equal in length to this scaled back blue vector. But in both cases, we get the sum of blue and red to make up to be the magenta. Now, if I wanted to be more specific, I could refer to this long blue vector as V1. I'll put an arrow over it to indicate it's a vector. And this short red vector is V2. And this scaled version of V1, I could call that A V1 because it's a scalar multiple. And this scaled version of V2, I could call that B V2. And then this magenta vector is A V1 plus B V2. So this magenta vector, which I'll call V3, I can say V3 is in the span of V1, V2. Okay? Now, I claim that the span of V1 and V2 is the entire plane. How can you see this? Well, think about a city and making city blocks, some roads parallel to V2 and some roads parallel to V1. If I did that, I could make a city block. So here's my, it's not quite drawn to scale, but let's say the reds are all parallel to one vector, to the V1, and the blues are all parallel to the V2. And you can see that with this arrangement, if this is my origin here, I can get anywhere from the origin. If I want to go here, I can follow this vector for this distance, and then up here along the other direction. If I want to get over here, I'd go back this direction along blue, this direction along red. Now, what about in between? Well, you can see in between, I would just go a fractional amount. If I wanted to get here, I'd go back this much and up that much. So by following these city roads that are parallel to my given vectors V1 and V2, I can get anywhere in the plane. So the idea is that two linearly independent vectors, and I'll talk a little bit about linearly independent, basically just means they're not in the same direction. They always span the plane that they are located in. All right, so that's what this says. Okay. So this is the first competency in the linear dependence relation section. So follow along with me. A linear dependence relation is a vector equation which has a non-trivial linear combination of vectors set equal to the zero vector. If all the vectors' coefficients are zero, the vector relation is called trivial. Okay. Now, before we saw about how to express that some vector is in the span of other vectors. So if I call this one V1, V2, V3, V4, this tells me that V4 is in the span of V1 v2, and v3. Right? Because I'm expressing v4 as a linear combination of v1, v2, v3. Now this is not a linear dependence relation. Why is that? Because linear dependence relation has a linear combination of vectors set equal to the 0 vector. I don't have the 0 vector on this side, so it's not a linear dependence relation. But it's easy enough just to take this vector to the other side, giving it a coefficient of -1. And then I have a non-trivial linear combination of vectors ending up with the 0 vector. Okay? So this spanning relation can give me a linear dependence relation. Okay? Spanning relation I can turn into a linear dependence relation. And actually, you can do the same thing vice versa. If I have this linear dependence relation, I could clearly put any one of these vectors on the other side, then divide by the coefficient, and that would give me a spanning relation. I relabeled this page up here because I want to make clear that this is concept 1 from the linear independence section. All right? Let's move on to concept 2. Set of vectors is linearly independent if there is no non-trivial linear dependence relation that involves only those vectors. Example, let's take these two vectors, 2, 1, and 5, 7. Sorry, the mouse is frozen. Try to find a linear dependence between these two. All right, now, that would mean that we would have some constant times this one plus some constant times this one, getting me the 0 vector. All right, so here I have a homogeneous system. X times 2, 1 plus y times 5, 7 equals 0, 0. We know how to solve this. We can write this as a system of equations. We know we can write it with the augmented matrix. We don't actually need the augmented matrix. We can reduce the row, the coefficient matrix. We know that the last column will be all zeros. When we row reduce this, turns out we get the identity matrix and the 0 matrix in the constant, and the 0 vector in the constant column. This tells us that the only solution to this homogeneous system is x equals 0, y equals 0. What does that mean? That means there's no non-zero x and y that gives me a linear combination of these two vectors that gives me the 0 vector. That means that this vector and this vector are linearly dependent. Okay, so I can just complete this by saying x and y are x and y are linearly independent because there is no non-trivial linear combination. That makes them 0. That adds to 0. All right? So that's the idea of linear independence. Okay. Clearly, you can generalize to any number of vectors. You can say that linear independence says something about the solution set of a homogeneous system. If the solution set is empty, then those vectors are linear independent. All right, let's go to the next point. This is concept 3 of linear independence. The columns of a matrix A are linearly independent vectors if and only if the homogeneous system LS of A0 has only the trivial solution. All right, so A is the coefficient matrix, and Z means it's a homogeneous system. Let's do an example. Okay, the columns of a matrix A. Here I have a matrix with 3 columns, 2, 7, 9, 3, 4, 5, 3, 2, 1, 1. And I want to know, are these 3 vectors linearly independent? So let me try to find a linear dependence relation. If they were linearly dependent, I could take some linear combination over here and sum them to 0. This gives me a homogeneous system. So here I form the augmented matrix. Again, the 0 column is unnecessary. When this row reduces, I get the identity matrix followed by the 0 column in the augmented matrix. And we know that this means that x and y and z are all equal to 0 is the only solution to this system of equations. This vector of equations is equivalent to this system of linear equations. Since there's only the trivial solution, that means that these vectors are linearly independent. Okay, concept 4. The columns of a matrix A are linearly dependent if the solution of LSA0 has free variables. And I should say if and only if. Well, that's what it says. It says otherwise the columns of A are independent. So columns of A are linearly dependent if and only if the solution of LSA0 has free variables. Now let's go back to the previous example and see how this works in the case of linear independence. Look at the solution of this system of linear equations. What did you get? You got the identity matrix and then all zeros. Okay. There were no free variables. That's why I got the identity matrix. No room for free variables. Okay, let's look at another example where there are free variables. All right, here's an example of a REF with free variables. Your free variables are Y, W, and U. All right, now, my claim is that these columns are linearly dependent. Now, how do I get that? Well, I can find a non-trivial solution to the homogeneous system. How do you do that? Well, again, the homogeneous system is equivalent to this vector linear combination equation where I put x times the first column plus y times the second column plus z times the third column and so on. If you write this out as a system of equations like we've done before and write the pivot variables in terms of the free variables, this first equation becomes x equals negative 5y. There's a negative because I pull it to the other side. Minus 6w minus 3u. All right, that's the first equation. Second equation becomes z equals minus 2w minus u. The last equation becomes v equals 0. All right, now, if I plug in any values of these free variables, I get a non-trivial solution to this linear dependence relation. Now, you might ask, what about the v equals 0? Doesn't matter. Non-trivial means at least one is non-zero. At least one is non-zero. So, for instance, I could choose y equals u equals 0 and w equals 1. If I choose w equals 1, then that would give me x equals minus 6 and z equals minus 2. And if I put those values in, x equals minus 6, y equals 0, z equals minus 2, w equals 1, u equals 0, v equals 0, I get this linear dependence relation. Minus 6 corresponds to this one here. This one's 0. The z is minus 2. The w is 1. U and v are 0. And that gives me 0, 0. This is a non-trivial linear combination of vectors from the set of columns. So that's a non-trivial linear dependence relation. Again, it doesn't matter that some of the coefficients are 0. As long as not all coefficients are 0, this is a non-trivial linear dependence relation. Okay, here's a problem. Determine whether the following vectors are linearly dependent. If so, then give a non-trivial relation of linear dependence. Right? So here I have these three vectors. Now remember what we have to do here. In order to determine linear dependence, we have to create the matrix A from these columns and find out whether the REF has free variables. Okay. So in this case, my matrix A, well, what's the size of matrix A? So A is going to be, well, here, let me do it in a different color so you can see that I'm adding stuff. So the matrix A will consist of these four columns. Now, what's the size of A? It has 3 rows and 4 columns. Now, remember, this is the coefficient matrix. So each one of these columns corresponds to a variable. So for this system, n is equal to number of variables, in this case is equal to the number of columns, n equals 4. And what's R? What's the number of pivot columns? Well, I don't know what R is, but I can have more pivot columns than I have rows. R is less than or equal to 3. Taking these two together, that means that N is greater than R. Now, we know when N is greater than R, that means we have free variables. As soon as I know I have free variables, I know that they're linearly, that I know that there's a non-trivial solution. As long as I know if there's a non-trivial solution, I know that they're linearly dependent. Okay? So without doing any work at all, I can tell that these vectors are linearly dependent. All right, now, here I gave a hint, add the first three vectors together. If you add the first three vectors together, 1, 2, 3, 2, 3, 1 plus 3, 1, 2, you get 6, 6, 6, which is 6 times 1, 1, 1. So in order to get a linear dependence relation, all I need to do is move this 6 times 1, 1, 1 back to the left-hand side. And I get a non-trivial linear combination of vectors is equal to 0, 0, 0. Now, the other way to find a non-trivial linear relation of linear dependence would be take this matrix, row reduce it, and then you would get there. Right. Just to show that you can do this by row reduction, I went ahead and put this into Python, and here's the result. From SymPy import star, A is the matrix here. You can verify that this matrix, row by row, is the matrix listed on the other screen. And then I take the REF. You can ignore this other code down here. It's just this code that we're talking about. And just to show you that this is actually the output, I'm going to go ahead and run this again. And you'll see that this is the matrix that I get, 1, 0, 0, 1, 6. So let's go ahead and copy it and interpret. I'm going to have to insert my space. We'll go down and we'll insert the screenshot and get this here. Here's my matrix right here. This tells me what? Move it over. This tells me that here I can say X, Y, Z, W. Let's make it a little bigger. So this will tell me that X plus 0Y plus 0Z plus 1, 6W equals 0. It tells me also that Y plus 1, 6W equals 0. And then Z plus 1, 6W is equal to 0. So I can just choose W equal to, might as well choose W equal to minus 1. And that gives me X equals Y equals Z equals 1. And those are the coefficients in this vector relation that gives me a homogeneous result. So that's where I get the 1, 1, 1. I'm sorry, instead of minus 1, I should have chosen minus 6. Minus 6. Now, if I choose W equal minus 6, you can see that I bring this to the other side. I get X equal 1, Y equal 1, Z equal 1. And I get exactly this relation. 1 times 1, 2, 3 plus 1 times 2, 3, 1 plus 1 plus times 3, 1, 2 minus 6 times 1, 1, 1 equals 0, 0, 0. Okay. So when you can't find the linear dependence relation by inspection, you can find it by row reduction. All right, let's go on. So this is the second competency in linear independence. It says, for matrix A, find a set of vectors that's linearly independent and spans the null space of A. So this is the same thing as expressing the solution of a linear system as a linear combination of vectors. Well, let's see how this works. Here's a matrix A. So I'll call this A. And let's see what we want to do. We want to find the homogeneous solution, so I need to row reduce it. Okay, and here, let me put it up here so I have more room. If I take the REF of that, well, I've got my handy Python REF, so first row is 3, 2, 1. Just change this one to be 3, 2, 1. Second row, 5, 1, 11. Third row, 4, 2, 4. Fourth row, 7, 4, 5. All right, and that's all I need to do. And I'll row reduce, and I get this matrix. Let's go ahead and snip it. I'll move it over here, and I think I need to get my typing set up, and then we'll have it there, and then we'll see if we can insert. And that's this matrix here. Okay, there we are. Make it bigger. All right, now what does this matrix mean? It means that I'm having trouble. There we are. What does this matrix mean? Well, I can get three variables out of this. I can call it xyz. This tells me that x plus 0y plus 3z is equal to 0. And this also tells me that y minus 4z equal to 0. And the other two rows don't tell me anything. Now, remember what I'm trying to do here. I'm trying to find a solution for the null space. Now, what's the null space? Null space is a set of variables such that this column times x plus this column times y plus this column times z is equal to 0. The x, y, and z that satisfy this is called the null space. So here I have equations for x and y in terms of z. This tells me x equals minus 3z and y equals 4z. I also have z is equal to z, so I can write this as xyz is equal to z times minus 3, 4, and 1. So what have I done? I've expressed the null space solution as a linear combination of vectors. In this case, it's only one vector, but it's still a linear combination of vectors. So the way you solve this type of problem is go ahead, solve the null space problem. You're going to get your basic variables in terms of your free variables, move your free variables to the other side, and form a linear combination of vectors that gives you the solution to the null space. All right, so that's the second linear independence competency.